to the notes where we were in chapter, and we truly are right about at the end of chapter 9. Okay, so here we go. Okay, so this is technically kind of the last slide. Can you guys see that?
Yeah, we can see it.
Okay, so I'll leave that up for a minute here. So C2H2, which is called acetylene, which they use in welding. So we're going to kind of look at this just like what Kara was asking about on that one on the quiz, on the number 4 on the quiz. But we're going to, again, describe the hybridization. And then we're also going to go back and we're going to do, count the sigma and pi bonds. So what it shows there here, and again, we're going to do the same process we've been doing. We're going to do the dots, and then we're going to count the. And actually, this one we've already done. I'm sorry, I screwed this up. I talked about this page, didn't I? Talk about this, Kara? Didn't I go over this?
Yeah, you did.
Yeah, okay, so here we go. This is what I wanted. I'm sorry, C2H2. I had the wrong page up. C2H2, acetylene. So again, I'm going to do the same process. I'm going to do the dots, count the electron domains. And again, you'll see here, well, you'll actually see a triple bond. So the first bond in a triple bond is going to be the normal hybridization. And then in a triple bond, the second and third bonds are going to be what's called unhybridized. Okay, so I'm going to kind of explain what I've got here there with those arrows and everything. Okay, so if I go back now, and again, I can go back to that slide if you need it. But so C2H2. And so if I do the dots, so carbon has 4 valence electrons. Okay, and I have 2 hydrogens. So I'm going to put one here, and then put one there. And then it's going to be this. It's going to be a triple bond. So if I clean it up, and again, that test will have in a couple weeks. I'll have at least one like this on there. So I've done the dots. So, and both the carbons are the same. But so if I count the electron domains, so there's 1, 2. Okay, now remember, 2 electron domains is sp hybridization. And this is really true of both carbons. Now, like I was saying, so the first bond, and like I talked about in the lesson posted yesterday, in a multiple bond, the first bond, what I think is the sigma bond, which is the stronger bond, which is located between the 2 nuclei, it's the normal hybridization. It's the sp. But in this case, these other ones are unhybridized. And since there's 2 of them, there would be 2 unhybridized. I don't know if I spelled that right. I'm gonna look this up. Unhybridized p orbitals. So Kara, kind of like that number 4 on the quiz. This is what I want you to do. So around, and both the carbons are the same. So they're sp hybridization with 2 unhybridized p's. Now, if I diagram that, if I go back to carbon and I do its electron configuration, so 1s2, 2s2, 2p2, what's going on here? What's going on? Well, in the so the 1s, the 2s, and the 2p's okay, so what's going on here with the bonding? Well, again, like we've been talking about throughout this chapter, one of these electrons promotes. So what I get then is I've got, and then these hybridize, because there's 2 electron domains. So we've only got 2 hybrid orbitals. So we have 2 hybridized SPs. And then these 2 are 2 unhybridized. They didn't hybridize. So here's 2 p orbitals, and they're just called unhybridized because they didn't hybridize. So here's 1 carbon. So here's, say, this carbon right here. Well, here's carbon 1. Well, here's the other carbon. It's the same deal. The other carbon, this carbon, is the same deal. It has sp hybridization with 2 unhybridized p's. So it's also like this. So here's the sp hybridized. And then we have H, which has the 1s1. And so here's how the bonding, what's going on. So remember, what this whole model, this valence bond theory, these localized electrons, is talking about bonding just orbitals that are half-filled. So here's going to be 1 bond. With, again, this is the normal hybridization. Here's going to be 1 bond. That's going to be that bond right there. Okay, then over here is going to be, again, 1 bond with the sp. And then the other bonds, here's going to be the double bond, and here's going to be the triple bond, if that makes sense. So again, if you go back and you count the electron domains, and remember, watch double and triple bonds. You'll see them actually, a couple of them on the Tinker Toy Lab, which I'm going to talk about here in a second, as well as when we do have the test, as well as the quiz you guys, well, the quiz you guys are going to turn in, there's going to be some double and triple bonds. Like I'm looking at number 3B on the quiz. 3B on the quiz. There's a double bond there. So you're going to have the normal hybridization plus 1 unhybridized p. Okay, and the final thing here is if I go back and I count the sigma and the pi bonds. Okay, and this is part of the lesson that I posted yesterday. And if you didn't watch it, you should watch it, okay? So what I said in a sigma bond and a pi bond, a sigma bond, first of all, is a bond between the 2 nuclei, truly the localized electrons. Sigma bonds are stronger than pi bonds. Sigma bonds are all the single bonds, and they are the bond between the nucleus, or in a multiple bond, they're the first bond. So the sigma bonds in this are 1, 2, 3. So there's 3 sigma bonds there. And the pi bonds are the second and the third bond in a double bond. So there's second and third. So this would have pi bonds. So pi bonds are weaker, and they're technically above or below the plane of the bond. So this would have 2 pi bonds. So this has 1, 2, 3 sigma bonds, and it's got 1, 2 pi bonds. Okay, I'd like to do one more here that is not in the notes. Questions there on that whole thing. So do the dots, describing the hybridization, and then predicting the sigma and pi bonds. Any questions there? Okay, so then okay, so let me do another one here. This is not in the notes, but let's say we've got this, C3H4. You know, and I told you guys since we started way back in August that I would really recommend the problems that we do in class to go back and redo them. This would be a good example of that. Just to go back sometime tomorrow, just go back and try this one. The dots are a little bit tricky, but we're going to do the same thing here. I want you to tell me the hybridization, and I want you to tell me the number of sigma and pi bonds, okay, in this molecule. Okay, so C3H4, a little bit tricky here in doing the dots, but I've got 3 carbons. And it's kind of tricky, like what do I do with the 4 H's? And this is truly like a puzzle and kind of just how you're going to fit a puzzle together. But I'm going to try and make it symmetrical. So I've got 4 H's, so I'm going to put 2 over here, and I'm going to put 2 over here. And so what it's going to look like then, we're going to bond here, 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 and here. And again, I've done this one. I did this one before class today. I would really recommend, like I said, you guys going back and trying this one again, either later today or tonight or tomorrow sometime, just for the practice of doing this. So now I'm going to pair up the single dots. So I'll pair up here, 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 and here. So it's all kind of messy. So if I clean this up, what I get is this. Okay, so now the hybridization. So I've got, we'll call it carbon 1, 2, and 3. Carbon 1, 2, and 3. So around this carbon, the hybridization, so if I count the electron domains, there's 1, 2, 3. So that is sp2. 3 electron domains is sp2. And because it's got a multiple bond, there would be 1 unhybridized P. This carbon would be the same thing, carbon 3, because again, it's got 1, 2, 3 electron domains and a double bond. So it's sp2 plus 1 unhybridized P. Okay, and around this carbon, carbon 2, there's 2 electron domains. So that would be sp hybridization. 2 electron domains would be sp hybridization, and then 2 unhybridized P's. And 2 is I got 1 on the left and I got 1 on the right. So there's the hybridization of that. Okay, now the sigma bonds and the pi bonds. So all the single bonds are sigma bonds. And the first bond in a multiple bond is a sigma bond. So the sigma bonds are 1, 2, 3, 4, 5, 6. So there's 6 sigma bonds. So 1, 2, 3, 4, 5, 6. And the pi bonds are 1, 2. So the pi bonds are always the second and the third bonds in the group. Okay, questions with that? Okay, so, okay, and I'll just move out of the way for one more second if you want to look at that again. Okay, and then let me just real quick, and I want to then talk about this Tinker Toy Lab. Okay, so if you look at the bottom of this, and it's covered up, but here are things you guys can be doing. You've got the quiz, which you need to get to me by tomorrow late night or Thursday morning. You've got the problems from the book. What it says on the bottom, it's 11, 13, 23, 25, 26, and 27. So there's other things you can be doing, textbook problems, 11, 13, 23, 25, 26, and 27. And so you can be working on the quiz. I'm going to talk about, and again, if you just got on, I think a couple of you did, I'm going to be talking next here in just about a minute. This thing, it says the Molecule Lab. I have this on both my Canvas page and my website. I think I put it under Tinker Toys, and I want to be talking about that. So that's another thing that you guys can be working on. This is just real quick. I'm going to go over this. I think this is kind of fascinating, one of these for your information. So we're talking about sigma bonds and pi bonds. In the human eye, light is detected by a chemical switch involving the breaking and reforming of pi bonds. Pi bonds are weaker. The back portion of the eye, the retina, is coated with millions of these light-sensitive rods and cones. Each of these cells contains 11 cis retinal. And I know it's difficult for you to see this, but this, again, kind of fascinating how this works. When a photon of sufficient energy strikes a rod or a cone, it causes the isomerization of the 11 cis retinal. So there's a change in just how the molecules are connected. The light contains enough energy to break the pi bond. Pi bonds are weaker. The sigma bonds, which is stronger, does not break, allowing to freely rotate about that bond. The pi bond then reforms with the molecules in the trans configuration. These cause electrical signal sent to the brain. I just think it's kind of fascinating how that works with the sigma bonds and pi bonds. Okay, I want to talk next about this. Okay, so the next thing, again, and you should have this in front of you. I'm giving you a week to do this. And again, if you had been here, I would have had you guys build these. But let me, because this week was the week we were supposed to be back, but of course we are not. But okay, so let me just do the first couple, and I'll talk about the shapes of each one of these. So I am on this Tinker Toy Lab, the Molecule Lab, and so we've got the Lewis structure. We've got the 3D shape, and again, I'm just going to try and help you with this as much as I can, and the polarity, the ABE, the shape, and the hybridization. Okay, so that's what we've got here. Okay, so for the first one, which is BCl3. So let me do the first couple with you. BCl3. So if I do the dots, whoops, that's in the wrong spot. So BCl3. So if I do the dots, I've got boron with 3 valence electrons. And then I've got chlorine like this. And so you would show it connected like that. Or you could have went back and done it the way I showed you, count the valence electrons. Remember, boron, beryllium, and hydrogen are those exceptions. Okay, so the 3D shape of this, then this would be, okay, so if I count the electron domains, 1, 2, 3, there's no non-bonded pairs. So this is the shape over here. We would call this, the name is trigonal planar. That would be the name of the shape, trigonal planar. The way I would diagram it is like this. This is the way, and I want to kind of go through the shapes and just how you diagram. This is truly the the way it would be a flat triangle. And if you guys were here and you guys could build this, you would see it would look just like this. Okay, and then this is just AB3. This is the family it's in, AB3. There's no non-bonded electrons. Okay, and then the hybridization with 3 electron domains, this would be sp2. Okay, let me do one more, and then I want to talk about the shapes. So SiCl4. So if I count the valence electrons, so silicon has 4, chlorine 7 times 4 is 28, so it's 32. So I get 32 total dots. So do the dots, count the electron domains. So there's 1, 2, 3, 4. So 4 electron domains is going to be the tetrahedral shape. This is the family AB4. Again, there's no non-bonded pair. If you had a non-bonded pair, that's an E. Okay, so this is how if you built this, what you would actually see is you'd see one of these chlorines coming towards you. And so again, I tried to talk about this earlier, but if you shade something in, it's coming towards you. And if you dash line, it's going away from you. And I'll talk about a couple of the shapes. But that would be the way you would diagram the tetrahedral shape. Okay, and one other thing I would say is if it's nonpolar, say NP nonpolar, both of these would be nonpolar. Those shapes are nonpolar, and everything would cancel out. And the hybridization here would be sp3. Let me go a couple things to the very last one. Let's go to the very last one. So it looks like this. So H2NOCBrHCOOH. Okay, so there it is. Can you guys see that? Mason, can you see that? Do I need to go down a little bit?
Let's drop it down just a tiny bit. Perfect.
Can you see it now? Okay, on one like this, the elements that form just one bond, they're going to be on the outside. So that's going to be the H and the Br and the H and the H, which means I'm going to write these in order. So I'm going to have N, and I'm going to go back and just do it the normal way. You guys can see that. So I've got N, I've got the oxygen. I've got the carbon. I've got the next carbon. I've got an oxygen. And I'm going to tell you something on this one. One of the oxygens is going to come here. Kind of help you out with this one a little bit. And then I'll put the other ones around it. So here will be H, H. The Br is going to go here. H. And there was another H that goes here. And I'll let you guys can kind of figure out a little bit how this is going to all connect. Now on this one, on this very last one, where it says the 3D shape, cross it out. You don't need to do that. You do on the It's the only one like that. You don't need to do the 3D shape. But I do want you over here where it says ABE, I want you to do the N, the O, and we'll call this C1 and C2. So I want you to tell me the family, the shape, and the hybridization for those. Okay, a couple things, just the final thing, okay, and then I want to move into chapter 10. Just kind of the shapes, the way you diagram the 3 dimensions. So I showed you tetrahedral like this. So the pyramid, so if you had to do the pyramid, this is the way the pyramid would look. So here's pyramidal. So you'd have one like this, and you'd have one element that's going to come closer to you, and then you're going to have like this. So this would be the way you would diagram the shape pyramidal in terms of showing one element coming towards you, and the circle is just any element. The way the trigonal bipyramidal would look, okay, remember we got the axial. This would be on the same plane, but then I would have one element that would be coming towards me, and then I'd have one element that would be going away. So that's the way I would diagram the trigonal bipyramidal. And remember when we get the seesaw comes off of the equatorial, the non-bonded pair goes in there. Okay, and then the octahedral would look like this. You're going to have, again, one that's going to come out towards you. You saw this in 3 dimensions, you'd see it. And then you're going to have 2 that are going to go away. Okay, hopefully that makes some sense. And then again, on Thursday, Friday, as you guys work on this, if you have questions or if you want to do a Google Meet and you have questions, we can do that. We okay? Okay, so then I'm going to move into chapter 10 then. So again, I'm going to give you guys a week, and not that you would need a week to do that, but just things you guys can be working on. So you've got the textbook problems, you've got the quiz. I'm going to give you another quiz before the week's over. You've got this you guys can work on. Okay, chapter 10. So here we go. This, in some ways, this is kind of a whole new chapter. This is going to be mainly on intermolecular forces, and I want to talk about this here for a second. Kind of reviewing big things from first year chem with this. But here are the problems to note for chapter 10. So here's more stuff that you guys can be working on. Okay, so let me kind of come back and review. I'll tell you what, I'm going to go to the next slide. Okay, I'm going to move ahead unless somebody objects. Okay, so here we go back to what we were talking about, really going back to chapter 8, because what we have been working on is intramolecular bonds, or bonds between atoms that make molecules, covalent, polar covalent, ionic. Now what we're going to be learning about in this chapter are bonds between molecules. So in a way, these go together. In a typical year, I would have tested you on 8, 9 in a normal year. And then 10, I actually was part of the first semester final. And I just made a bigger portion of the final on chapter 10. And intermolecular forces are a big thing on the final. There's no doubt about it. Or a big thing on our AP test. Okay, and this will be the last slide, but I want to do a little bit of review of what we, again, intra versus inter, and then kind of review of what we learned earlier, what we learned in first year Chem. Okay, so I'm going to go. Okay, so so if I diagram this out, so just the difference again, and not that you wouldn't be good with this, but just the difference again, the intramolecular, which is what we've been learning about pretty much since we got back from vacation, versus inter. Hey, Jen. So if we have H connected to Cl, this right here is the intramolecular force. And that's what we've been working on. Well, if I have another HCl, this is the intermolecular force. And so what we're going to be learning about in chapter 10 is this force right here. And one thing to note is that bond there, the ionic, the polar covalent, or the covalent, is always stronger than any of these. It's always stronger than any of these. So let me kind of go through what I do with my first year chemistry students in this. And to me, it works in our class, but just like always, we're going to go into some more definitions. But under the intra, so just reviewing what we just did, because these two are going to be connected. And the way in chemistry they always abbreviate the inter, what we're going to learn about is IMF. So what we had for intra was we had ionic, we had polar covalent, and we had non-polar covalent. So quick review. So I said, we don't have an electronegativity table in front of us. So ionic is when we have a metal and a non-metal. So we're truly just using the location of the elements on the periodic table. So ionic is when we have a metal and a non-metal. Polar covalent is we had two non-metals, but one of those non-metals is NOF or Cl. Okay, I'll say it again. And I said this a lot the last couple of weeks. So polar covalent is when we have two non-metals, but one of those non-metals are that upper right-hand section, the NOF or Cl. Non-polar covalent are when we have two non-metals, but it does not include NOF or Cl. Okay with that? Okay, so now on to the inter, what we're going to learn about. So I'm going to kind of show you, if you remember this, it's going to help you as we go through this. And technically I'm lying to you, but there's really not an intermolecular force that's ionic, but we're going to treat it that way. Okay, now again, I'm going to preface that there's really not an intermolecular force that's ionic, because An ionic crystal is this huge crystal of these alternating positive and negative charges. And, but we're going to treat it that way. So it doesn't really, it's like a huge massed molecule. Well, polar covalent, and that is actually number one. That's going to be the strongest intermolecular force, okay? Then for polar covalent, there's really two possibilities. One is a hydrogen bond, an H bond, which we'll review that. Okay, and you might remember this. A hydrogen bond is whenever hydrogen is bonded to NOF. And I call those the NOF buoys. I was actually taught that by a student teacher I had a few years ago, and it was a really good way to remember it. So nitrogen, oxygen, fluorine connected to hydrogen makes an unusually strong bond. And if it's not that, it's then called dipole-dipole. Okay, and I'm numbering these in terms of strength. And usually, typically, in first year chem, I'm always doing this about the time that March Madness is occurring. So I always talk about the tournaments and the brackets and everything. And then this would be what's called London dispersion forces. It's also called van der Waals forces. And again, we're going to talk about all this stuff. But I'm kind of giving you the overall big picture here, because I think it's going to, if we can remember this, we're going to be in pretty good shape as we go through this chapter. And again, we're going to go into more detail, definitions, and we're going to get into that starting tomorrow in the lesson I'm going to post. But the stronger the intermolecular force, so the ones with their higher number, they're going to have a higher boiling point. They're going to have a higher melting point. And if you think about it, that makes sense, because you're saying it takes more energy to break those apart. They're going to have this thing I'm going to talk about, the surface tension. We're going to talk about in this chapter, which will be something new, is going to be higher. The viscosity, which is another thing I'm going to talk about in this chapter, is going to be higher. But the vapor pressure, which is always a key one, it seems like it's going to be lower. And also the volatility is going to be lower. Volatility is how quickly something evaporates. And it might be a good idea just to review that, to take a picture of that. And that is a good place to lead off on. Cleaning the floors of school. Looking forward to you guys coming back. Okay, so again, you guys have to get me the quizzes just by the time I open up my email on Thursday morning. Okay, you got the problems now from chapter 9 to work on. I'm going to post a lesson for tomorrow in chapter 10, so you can be looking at that as well. So you've got a lot, there's a lot of AP chemistry you guys can be working on. So, okay, any questions you guys have? Joke, up, down, up, down. It was a downer. Didn't like that one. Kara liked it. It was up, okay. Well, for those of you that are awake, good day. For everybody else, wake up. It's time to wake up. I'll see you guys on Thursday.
Thanks, Mr. Wood.
Have a good rest of your day, Mr. Wood.
See you guys.
Thank you.